Okay, so let's start today's lecture. So when you check the course site on Sakai, when you go to week 4, so on week 4 we have all the contents of this week's topic, which is the violation of OLS assumptions. And as I said last week, today's topic is a mix of different chapters. Okay, so different sections from different chapters. So we have some parts from chapter 4 and 5 and 6 and 7. Okay, so it's very important to follow the reading list so that you're not lost on where you would be able to find the materials to read more about it. Okay, so you have the slides here. The slides, again, it's just a mix of different sections. This video here is an old video of mine. It's kind of very old, actually, but I still find it important because it would give you another example of how to estimate a model using the growth data set. Okay, so it's important to check it out. And then these are more recent videos, and today we're going to discuss the M-test, and we're going to talk about heteroskedasticity tests. And here you have a practice non-graded question. I want you to watch the 2 videos. Both are related to the SAT exam dataset. What are the factors affecting the SAT score? And after you're done with watching the video, I want you to take the practice. As I said, it's non-graded, but I will use it as extra credits. Okay, so each practice worth 3 points, which would accumulate, like would give you, like, so far we have 3 practices, so 9 points. So it's great that you can just watch the video, and the video would give you like a step-by-step instruction on how to estimate the model. After you're done, you can just click here and take the practice. It's kind of a replication of what I'm doing, so it's not like something that you would find too challenging or anything. Okay, today we're going to have a practice during our class, and I sent you by email the CPS 12 dataset, which is the Census Population Survey of 2012. At many times when I post datasets on Sakai, it doesn't read it. So sometimes when you click here, you will not be able to get the file. And that's why I sent it by email before our class. Okay, and that's what I'm gonna do every time, because I just want to make sure that you guys are able to get the data set. Every time we have a data set, I'm sending a data description, because the data set has abbreviations. You will not be able to understand, okay, what is IN until you read the description. Okay, IN means income. Okay, and each data set has its own abbreviations. So that's why it's very important to read the data description. It would let you know if this data is related to an actual research paper, related to an actual project, or related to, okay. Your homework of this week has 2 parts. And as you can read the description here, I mean the instructions here, right under the title of homework 2 part 2, the homework has 2 parts. And this is going to be the case for all coming homeworks. So part 1 is on MyLab, similar to the questions that you have seen on homework 1 and quiz 1. Okay. Part 2 is the Stata application. So if you are able to go over the practice questions on Stata and kind of like practice it enough to be confident about how to estimate a model using the software, then you should be fine with part 2. Okay, and remember, and I'm going to add this right here to the instructions part, is every time you're doing any Stata exercise, you have to post for me the do, which is the code, and the log, which is the results files, okay? Because otherwise, I'm not sure how you got the results. So I need to run your code, get your results using your own code, okay? So make sure that you go to your Dropbox and you upload your do and log file. And as I mentioned multiple times, the log file is simply a text file. So it has an extension .txt. The data that you need for the homework are available in Excel and DTA, and I can always provide it in CSV. Okay, and then again, here is the data description that would let you know each abbreviation stands for which variable. After you're done, after the due date of which is after the 27th, I will post for you the code right here. And remember, we have a discussion for this week. Each discussion, you have to remember that you are graded based on 3 parts: the timing of your post, the date of your post, and whether you are interacting with other students in your class or not. So you have to post at least 2 response posts to your classmates' posts. Okay. All right, so what I'm gonna do now is I'm going to share the iPad, and I'm going to go through our topic, which is the violation of the OLS assumptions. I'm gonna start with the OLS assumptions, what are the assumptions, and then how we are violating it and how it's going to affect our model. So let me go ahead to the iPad.
Hey Miss, I think the other kids are on a different Zoom meeting. I got it, and they said the kid off me is with Parth and some other kids, and they're waiting on you.
Oh, really? Another one?
Yeah, another one. Yeah, he said it's just them. That's why I thought it was kind of weird that it was just us two on here too. But
That's
yeah.
so weird. Okay, let me find that out. Okay. Did you click on the same link that I sent last week?
Yeah, that's the one I clicked on. Yeah.
Okay, so let me try to, okay, just a second. Are you seeing my iPad now?
No, I'm still seeing. No, it's normal. It's just you.
Okay. No, something is weird today, so I'm just trying to figure out what's going on. You know what? Let me, okay, let me try to see how can I get them.
You could probably just send out like another email and click another link, and we can just get out of this one and start a new one. I think that'll probably work.
Uh, you mean the same one that I sent last time, right?
Yeah.
Okay, I have it here. I'm gonna copy the link and I'm going to go and send it to them. Okay, let's see.
Hello,
Yes, hi, who's this?
Othman.
What happened? Did you click on the same link I sent last time?
I clicked on the link from the first class, assuming that that's the one that we were going to be at. Park, and Daniel, we were all in that same one.
Oh, okay.
Yeah. So we kind of just thought that you weren't there, but then I went and clicked on the most recent one that you sent us, and that's when it brought me to here.
You mean of last week or the one that I just sent right now?
No, of last week. I
Oh,
just
yeah.
right now. Yeah.
Okay. Yeah, sorry about that. I was like saying, okay, where are the students? So I found only
Uh,
one.
yeah, we were there, and the other one just me, him, and Parth. Me, Dan, and Parth for like since like 12:30, just waiting. I even
Wow.
texted Lewis to see if he was in the. He's the one who
Okay.
just checked the other
Okay,
messages.
so I'll make sure that I thought, okay, you guys have the link. So maybe I used a different link on the first meeting.
Yeah, but only the very first meeting. The rest are all the same.
Mm-hmm. Yeah. Okay. Okay, we're still waiting for Parth and Daniel, right?
Yes.
Okay, so let's continue until here. Okay, he's here.
Hey, Miss, did you want to repeat that part about the homework and how like you have to show like the log stuff?
Mm-hmm. Oh, yeah. Who's talking? Lewis?
Yeah, I don't. Yeah.
Okay. So let me go back to the desktop.
Also, did that quiz that was posted on Pearson, is that actually a quiz or is that another like practice?
Okay. Pearson, you're saying?
Yeah, the one that was on my labs.
So there was a quiz on Friday, right? Is this what you are talking about?
Yeah, I had assumed that it was on. Well, it was just my wrong assumption, but I just assumed it was on Sunday.
Okay, Osman, you sent me an email, right?
Yeah.
Yes, I remember now. So actually, uh, so what I want you to do is you print out the syllabus and you have all the dates there. Okay, so you will see that all our quizzes are on Fridays.
Okay.
And yes, we had a quiz on last Friday. I think you and another student, I can't remember who, one of you guys sent me an email saying again they missed the quiz. So yes, I want you to print out the syllabus and make sure that you're not missing anything. For the one that you missed for last Friday, I'll give an exception for you. And I can't remember who
Yeah, I
else.
didn't. Yeah, I didn't do. I didn't get to do it either.
Okay, Louis, yes. So I think both of you have sent me an email. So I'll open it for you guys again, but just remember it's one-time exception because you have all the dates on the syllabus, okay?
Yeah,
I
no problem.
really
Okay.
appreciate it. Thank you so
Okay,
much.
so I'll do that right after our class.
All right, thank you so much.
Mm-hmm. So again, yes. Oh my God. So now it's 12:50. So we missed 20 minutes. uh, I'll make sure that I'll send a link right before our class every time, but just make sure it's going to be the same link. Okay. It's maybe the very first time I use a different link until I had my account set up on Zoom. And then I started to have just one link for everything to make our life easy. Anyways, I started today's class by talking about everything is going to be recorded, so which is good. So I'm just going to briefly go over the main points here, but everything is recorded, so you don't have to worry about the details of what I'm talking about. I just went over week 4. Okay, and I mentioned that week 4 is a mix of the 4 chapters, 4, 5, 6, and 7, different sections from each chapter. And And it's very important specifically for this week's topic, because not all our topics are a mix of different sections, especially this one. Because when I was like checking your textbook, I felt like, no, it's better to combine the violation of all else assumption into one topic. So that's why I realized I ended up by referring to 4 different chapters. But make sure that you follow the reading list so you're not lost. You have the slides here. You have a very old video here of mine. I don't remember, this was like probably 2000 and maybe 12 or something, but still it's important, and it would give you an additional information or additional example on state. The M test, we're going to do it today, and heteroskedasticity tests. As I mentioned, we already have in the previous weeks practice 1, practice 2. These are non-graded, but I would like advise you to do it because this would help you for your midterm. This would be like an extra credit. I would consider it as extra credit. So each of these practices would worth 3 points. So keep accumulating the points, right? So if you do this one and plus the other 2, so you have a total of 9 points. So far, I have only 1 student who submitted the practice, okay, or 2 practices. So just make use of these points because I don't want you to regret it, okay? Because these are, you would watch the video and you would actually replicate what I'm saying in your practice, okay? So try to make use of that. In today's class, we're going to be using the CPS, which is the Census Population Survey 2012. It has the description right here. And as I mentioned previously, that at many times the data, when I posted on Sakai, when you click on here, it doesn't download for some reason, like Sakai does not accept the data files. So at many times you would find me, or most of the times you would find me emailing you the data set. Okay, you have them here. For some computers it works, but for my Apple computer it doesn't work at many times, and I have seen that.
Yeah, for some reason I can open the second link, but not the first one. It won't
Yeah,
let
the
me.
second one you can open it because it's a Word document. It
Yeah.
has an issue with the Stata files. This is a .dta file, which is the data file of Stata. I think if you have a Mac, do you have a Mac computer?
Yeah.
Yeah, same here. So yeah, when I open it, it just like it shows me like a Chinese letters or something.
Yeah, like a huge code.
Yeah. So that's why you can check the email and download it from there. Homework 2, I still have to post for you guys the link here. I should do that by tonight. And make sure anytime you have homework, you have to submit the do, which is the code, and the log, which is the results file. Because I would run your code and compare it with your results and grade, okay? So you have kind of 3 things to do when it comes to part 2. You have to submit the multiple choice questions when you click on this link, and you have to submit the do, and you have to submit the log files. And if you do not submit the do and log files, I will not be able to grade your part 2. So make sure that you don't forget that. I will actually add it right here so that you do not forget.
This is
Okay.
the first homework that we have using Stata though, right?
Exactly, yes. Homework
Okay.
1 was just 1 part on my lab.
Mm-hmm.
Starting homework 2, we're going to have it in 2 parts. All homeworks are going to be on 2 parts. Parts that you will submit on my lab, and the second part, which is the Stata part, on Sakai.
Okay.
Mhm. All right. And then remember that you have a discussion this week. You have to follow the rubric on your syllabus so that you're not missing anything, okay? Because I'm grading the discussion under 3 main parts, which is your initial post, your response post, the timing of your post, okay? And the later in the week that you post, the less and less and less you grade. So make sure that you post earlier in the week and you follow the rubric, because each day has a different grade. All right, so let me go back to my iPad so we can start our today's lecture. And again, anytime you have any question, just stop me. Okay, so today's topic is about the violation of the OLS assumptions. Okay, and OLS is the ordinary least squares. Okay, and we're trying, like, you go back to your notes, which is about trying to minimize the sum of the squared errors, right? This is our main objective, is we're trying to minimize the amount of errors that we have in the model. And this is subject to all the coefficients that we have, beta naught, beta 1, all the way to beta k if I have a large model. So ordinary least squares, because we have different types of estimation methodology. The one that we're discussing today, or actually week 1, week 2, week 3, week 4, is actually about the ordinary least squares. So in today's topic, we're going to talk about the violation. And before we talk about the violation, I'm going first to go over the assumptions. So what are the assumptions? The OLS assumptions are mainly 4. If I have a model like this, yi is equal to beta naught. Does anyone have any problem with the color yellow on a green background?
No, I'm fine.
If anyone have any problem, let me know. I can change it to black. Okay, so you're not saying anything? I assume that you're fine. Okay, beta 1, x1i, and then we keep going until we get all the factors that affect y, beta kx, ki, plus an amount of errors. Okay, and this is, we said this is called the population regression line. We get our data set and we estimate the model. We get the yi hat, which is based on all the hats, right? Beta naught hat plus beta hat 1. Xi doesn't have a hat. This is just the data set that you have, plus beta hat k, x, ki. And the difference between this one and this one would give me the amount of errors. Or you can say here that this one is the sum of the difference between yi minus yi hat, you square it. So the difference between these two would give me the amount of estimated errors. So this OLS assumption is based on a very important condition, which is the expectation of the amount of errors given x1i, x2i, this is 2, x3i, and keep going, xki is simply equal to everything about the error term is simply equal to 0. What does that mean? So it means actually that any factor I have in my model is not connected with the error term. They have no relation. So the expectation or the conditional mean from your statistics course, or if you have taken the foundation of econometrics course, you would know that this is called the conditional mean. So this is the conditional mean, which is the mean of the error term conditioned on the values of x1, x2, x3, all the way up to xk. So this conditional mean is simply equal to the mean of the error term. In other words, having the values of x does not mean anything, because there is no connection between the factors included in the model and other factors. I wanted to think about the error term as anything that you didn't include in the model, right? You can call it error term, you can call it other factors, right? So there is no connection between the included x's and other factors which are excluded from the model. So this means that other factors contained in the error term are not related to the x's included in the model. Okay, so if you give me any value for x, the mean of the distribution of these factors is 0. And this has an important implication, which basically says that, okay, this means that there is no connection between the error term and x. I'm going to write it as xi, but you can change it for x1 or x2 or x3 or xk. So the covariance between ui and xi is equal to 0. And if the covariance is equal to 0, then the correlation, the correlation is actually made out of the covariance. In order to get the correlation, you have to compute the covariance. And if the covariance is 0, then the correlation is also 0. Okay? So when you look at this slide, you might be like, okay, I don't understand anything. But the idea is very simple. The idea is, if I have average hourly earning, which is like salary, for example, or the wage, average hourly earning, as a function of age, okay, and that's it, and this is the error term, and this is I, and this is I, based on the assumption that I have just discussed, it simply says that there is no connection between other factors that I'm not including in the model and age. It's simply equal to everything about other factors, which is equal to 0. Do you get that? In other words, it might not be, like, it might be unrealistic, right? Because here I have education, I have experience, I have what else? Gender. I have so many other factors that can affect the person's salary, or can say other things, right? So based on this assumption, if I replace this UI with education, because education is not included in the model, that's why education is included in the error term. So if I can say, okay, does that mean that education and age is equal to everything about education is equal to 0? Yes, this is what this assumption means. There is no connection between age and education. There is no connection between age and experience. There is no connection between age and gender. So it might be unrealistic, because we know that as the person gets older, the education or the years of schooling increases. There is a positive relationship. Might be also true that there is a connection between age and experience. Okay, whether there is a correlation between age and gender, it all depends on my sample. So if my sample is more towards female, and the females I have are older than the sample of males I have, then there might be a connection. Okay, so this is our first assumption, and all the assumptions that I said, we have 4 assumptions, and all the assumptions that I will mention now might not be realistic. And that's why we call it assumptions. We're gonna just assume it, and then we're going to drop it to see how we can how we can deal with the problems that might arise after we drop these assumptions. Number 2 is xi and yi. This set of x's are independent, identical or identically distributed. And this is what we abbreviated as IID. So the set of x's I have and the set of y's I have are independently, identically distributed. So what does that mean? So if I have this population and I'm trying to build or take a subset of it, and I call it a sample, and the population, let's say, is 500 people, and I'm just making a sample of 50. Now, every person I pick out of this population and take it into my sample is purely random. Okay, so each and every person in this population has the same chance of being selected. So in statistics, we actually say it like this: the probability of selecting person 1 is the same as the probability of selecting person 2, is the same as probability of selecting persons 3, is the same as the probability of selecting person n. They are all the same. So in statistics, we say they do have same marginal probability, same chance of being selected from the population, okay? And if this happens, then we call it identical. They do have the same or the identical probability, identical marginal probability. And this is about this word, okay? They are identically distributed. What about independence? So if I, of course, you can repeat this on the X, okay? Because if I pick the salary of person number 1, it has the age of that person with it. So you can repeat this one with the probability of X1 is the same as the probability of X2 is the same as the probability of XK. How about independence? Independence actually means that if I pick person number 1 and ask him or her about the salary, and I kind of record the response, this would give me zero information about the second person's salary, right? Each and every person is completely independent. And in statistics, we say it like this: the probability of picking person number 1, given any information about person number 2, is simply equal everything about person number 1. That's it. In other words, you say the conditional probability of y1 is equal to its marginal probability of y1. Okay, again, it might, like, you might look at this and say, okay, I don't understand it, but the idea is very simple. Give me the probability of picking person number 1, give me any information about the salary of person 2, it will give me nothing, right? It will help me nothing about the probability of 1. It just would give me probability of 1. You can repeat this with every other observation. Okay, so you can again like say, okay, the probability of picking person 3 given person 2 would give me everything about person 2. No, 3, the first one, I'm sorry. Okay, would give me everything about 3. Okay, or you can make it random, I and j. Probability of I given j would give me I. All right. How can we apply this to our models? So if I'm, like I actually gave you an example. So if I'm talking again about the average hourly earning, okay? And the average hourly earning of different people, person number 1, person number 2, person number 3, person number n. The response here does not, like, will not help me to get any information about this person, and this is not supposed to give me any information about this person, and so on. So when I talk about cross-sectional data, this is easily like achieved, right? These assumption, or this assumption is easily achieved when I talk about cross-sectional data. A group of students, let's say here in this class, if I check what you got for homework number 1, before I open the homework number 1 for another student, I have no information. They are totally unrelated. This class is a cross-sectional, a group of people, right, in a single point in time, which is, let's say, the fall semester. However, this is not like it, this is easily applied here in a cross-sectional data. However, in time series data, this is not applied. Like it's usually violated. So if I'm talking about, let's say about the virus, right? What happened with the virus, with the virus since March until now, okay? And what happened to the economy, GDP? What happened in March is connected with what happened, right, in April, what happened in May, right, what happened in June, in July, in August, in September, because I'm talking actually about the same variable and over time. So if you give me information about March, it would help me to predict information about May. It would help me to predict information about September, right? So in time series data, it's very, very hard to say GDP of March is not connected with GDP in April, is not connected. And the same applies with most macroeconomic data set. Okay, so anything that has time series dimension, it's very hard to apply this assumption of IID. Okay, our third assumption is kind of, it will not take time. So our third assumption is about outliers, large outliers are unlikely. So if I have a data here, okay, and again, assume this is the average hourly earning, and this is the person's age, and I got information about 10 people, so I'm gonna have 10 dots, right? So the first person is here, and so on, okay? And as you can see, I can group these observations in a kind of an oval shape, and I probably can fit a line that says there is a positive relationship between, right, age and average, between age and average hourly earning. As you can see, I don't see any point that is outside the range of observations. If I have a dot here, an observation here, this is called an outlier. If I have a dot here, this is called an outlier. So anything that is outside the range of observations, we call it an outlier, okay? So we assume that when we're trying to estimate a model, we do not have any problem with having large outliers. We assume that you graph your data set, you check your data set, you make sure that you don't have anything weird, anything that is outside the range of observations. And if this happens, you go there and you check why. Is it the case because my variables are in dollars and one of them is in cents, so it's going all the way up here? Or is it related to anything that is, for example, the government has changed the policy, the government has increased the money supply in a specific year? Anything that is important, we're going to take it into our consideration. Anything that is related to a mistake, we're going to deal with it, or probably we're going to correct the mistake. Or probably we can simply, if it is not that important, so we can just delete any outliers from our model. Okay. If it is important, as I said, then we're going to talk about how can we include it into the model. But I'm assuming that here it's a data point that is outside the range of observations that is not needed. So I'm going simply to delete it. Our last point is, or the last assumption is about no perfect multi-collinearity. What is multi-collinearity? Okay, there is an I, let me write it just. So multi-collinearity is all about the axis. So if I have a model, so it's all about the connection between the axes I have in the model, okay? So perfect multi-collinearity means that the correlation between x1, x2 is 100%, is equal to 1 or -1. I don't care about the sign now. It's 1 or -1, it's 100%, okay? If this happens, then I will not be able to estimate the coefficients beta 1 and beta 2. Okay, so perfect 100%. So we assume that we don't have any perfect multicollinearity. We can have imperfect. What is imperfect? Imperfect is anything that is less than 100%. It could be 99%, it could be 98. And if I have this imperfect multicollinearity, which we can see it in our models, we're going to deal with it. We're going to overcome it. We're going to detect it, find it, estimate it, and overcome it. But our assumption is saying I don't have anything perfect. Okay, which is like really bad problem. Okay, so we have no perfect multicollinearity, but we are allowing for imperfect, less than 100%. Okay, so if I do have these four assumptions satisfied, okay, so I have no connection between the error term and the axis in the model. I have IID data set. I have no large outliers, and no perfect multicollinearity. If this happens, then we're going to have, like, if you have all the assumptions satisfied, then we're going to have something called the best linear unbiased estimators. Okay, and this is abbreviated as BLUE. Best linear unbiased estimators. Okay, so if all assumptions are satisfied, then this is like the perfect world, right? And then I can say that I will get the best linear unbiased estimators. In other words, the best linear unbiased estimator consists of three important parts. It has to be unbiased and it has a test. It has to be consistent and it has a test. And it has to be efficient. And again, it has a test. So what is unbiased? Unbiased is it simply says that my expectation of the coefficient, and I can just make it general and call it J, is equal to the truth. The expectation of the coefficient that I get from my sample is equal to the population coefficient. So this is the actual. Population is the actual, right? The truth. You can call it the truth. Okay? And this is the estimated using Stata or any other statistical software, or probably by your hand if you're doing a simple model. So unbiased means that the coefficient that I estimated is simply equal to the truth. Okay, and I want you to just repeat this for each and every beta you see. I'm saying beta J, but you can repeat this for the intercept, beta naught, partial slope 1, partial slope 2, partial slope 3, and partial slope k, right? So this is number one. So unbiased means that the expectation is equal to the truth. Consistent is actually very similar to unbiased, but it adds the idea of maximizing the sample. So consistency simply means that, okay, I can achieve this if I maximize the sample. And this is actually makes sense, because if I want to get the most accurate estimation, I have to maximize the data set as much as possible. So consistency, it adds that as n, which is the sample size, n is the letter I use for the sample size, as the sample size increases, the beta hat J would be very close to beta J with a very high probability. Okay, I'm gonna repeat it again. Consistency is very simple to unbiasedness. But unbiased, you can think of it as a single point in time. This is equal to this. No, consistency is more about, okay, to achieve this with a very high probability, just maximize your sample size. So it says that as the n increases, this is an arrow and ES, as the n increases, beta j would approach the truth with a very high P, which is very high probability, could be like 90%, 95%, 99%. Okay. What about efficiency? Remember, this plus this plus this would give me blue. Like I can't have one of the components. It has to be and. Okay, or and, unbiased and consistent and efficient. What is efficiency? Efficiency is related to the variance, okay? So the variance of the estimator. The variance of the estimator. So if I have a choice between beta hat m and beta hat n, two estimators, and two are the slope of the age variable. Okay, so I have like here AHE is equal to beta naught plus beta age. This beta can be beta m or beta n, like two numbers. Which one is better? Should I go with beta m or beta n? And this is like an estimated model. So I have the hats here and I have two options here. Which one is better? So based on efficiency, the best estimator is the one that has the lowest variance. Okay, so you want to pick the estimator with the lowest variance. So let's say here I'm going to compute the variance of beta hat m and compare it with the and you compare it with the variance of, and this is versus the variance of beta hat n, and you pick the lowest variance. Okay, so an efficient estimator is the one that has the lowest variance out of all possible or all available estimators. Okay, so if you combine these two together, I want you to think about it like this. Remember, the T statistic was like how far my estimator from the truth over the standard error, which is computed from the variance. So the first two are related to the upper part of the T statistic, which is how far the estimator from the truth. The third one, which is efficiency, is related to this one, which is the standard error of beta j. So when you think about the test statistic, it's all made out of the three components of an estimator being blue. I need an estimator to be unbiased, consistent, and efficient. And if any of these are, like characteristics of a good estimator is not satisfied, then I might have inaccurate estimation of the T statistic. And I'm sure that you know that if the T statistic is inaccurately estimated, the p-value, which depends on if it is a two-sided test, right? Which depends on all the points that are less or equal to the T statistic. So if this is inaccurately estimated, then the p-value, because I take it and I plug it in here to get the p-value, then the p-value is inaccurately estimated. So I would get like misleading results on all my test statistics. And if you remember, this one is used in the confidence interval, because the confidence interval is beta hat j plus or minus the standard error of beta hat j times the critical value. So if the standard error is not the lowest, then the confidence interval would be widest than it is supposed to be. And if it is wider, I should say wider, not widest. It would be wider than it's supposed to be. And if it is wider than it's supposed to be, it might be including the zero number. And remember, if the zero is here, if my confidence interval is supposed to be between these 2 points, and because of the wrong standard error, it's wide, so it's wider and it comes here, the 0 might be included. So you might actually fail to reject a null when you're supposed to reject it. Okay, so what I want to tell you is one mistake would lead you to another mistake, and one mistake would lead you to an inaccurate estimation and an inaccurate results. Do you have any questions before I move on to our first violation? Any questions? Okay. So when we talk about the violation of the OLS assumption, we talked about the assumptions. I was actually supposed to talk about the assumptions last week. I didn't have the time. So these assumptions, or these 4 assumptions, can be actually in real life violated. That's actually most of the time it's violated. We don't live in this nice world where we don't have any connection between the variables in the model. Actually, each and every variable is so connected, especially in macroeconomic data set. So when I talk about the violation, I will talk about 3 important parts. The first one is called heteroskedasticity. Second one is called multicollinearity. The third one, let me write it here, is called misspecification errors. If you have taken with me the foundation of econometrics, I know 2 of you have taken the foundation with me, you would see some titles are repeated, but not the contents. So the notes would be very helpful, and you can actually share it with the rest in the class. But the contents, the contents in this course are definitely deeper. So for heteroskedasticity, we're going to start with heteroskedasticity, move to the multicollinearity, and third is misspecification errors. I might be too optimistic if I can cover the 3. Okay, I'm supposed to cover the 3 in today's class, but I don't think with about 30 minutes we lost in trying to find each other at the beginning of the class. So let's see. So what is heteroskedasticity? The first part, hetero, means actually unequal, and skedasticity, it's a Latin word and it means variance. So it's a problem of unequal variance. Okay. We know, based on the assumptions I mentioned, is that there is a critical assumption of the classical linear regression model, is that the error term will have same variance. So the OLS assumes that the error term, or U, has same variance all over the data set I have. Okay. If this happens when I say same variance, we say homoskedasticity. So the OLS assumes that we have homoskedasticity. And if this assumption is violated, which means I don't have the same variance, I do have unequal variance, then I have a heteroskedasticity problem. So what does that mean? So let me show you an example. Something like this. So imagine that you're talking about income and the amount of rent paid, okay? And assume that I have a group of people of 1,000, and I take each person and I ask 2 questions. What is your income and how much you pay for your rent? And I take the 2 observations per person, and I'm gonna have 2,000 observations, right? And I'm going to ask them, okay, I'm going to report these here. So it's gonna be I'm just making anything, okay? And this would tell us that, okay, there is a positive relationship. As the person's income increases, he or she would pay more in the amount of rent. And when you try to look at the distribution, okay, it looks like normally distributed. I should like have a nicer graph. Okay, normally distributed, right? So I have like the distribution is constant all over, right? Okay, it doesn't seem to change. So this is called homoskedastic. And this is what the OLS assumes. It assumes that constant variance, the variation of rent, with whatever income level is constant. I'm gonna write it like this: the variance of rent, if you give me any level of income, is constant, and this is called homoskedastic. However, in real life, we know that this might not be true, because it might be the case that for rich people, right, you have options, like you have wider options. I might be rich and I still want to live in a condo, or I might be rich and I want to live like in a huge mansion, right? So you have options, and it all depends on your taste. However, if someone is from the low income group, you don't have options. So you're going to be limited with certain amount of income and certain amount of rent. So we would expect this relationship to start tight and then it gets wider, right? It gets wider. So yes, it's still positive. We don't say anything about the direction of the relationship. Again, as income increases, rent increases, but it makes more sense that the variation at low levels of income is kind of tighter than at high levels of income. So it gets, I'm sorry, I should have like a nicer graph, but it gets wider and wider because people get more and more and more like options. Okay, I wanted to repeat this idea with so many different things. Okay, if I have a small class and the test score, usually if I have a small class, the variations within the class is small, but if I have a class of 1,000 people, the variation will be wide. Okay, you can also think about so many different examples. You can remove the rent and think about consumption. Okay, so consumption, if I have a low income group, then the amount of income allocated to consumption would be smaller. Variations between people in this income group would be small. However, for people who are rich, the amount of consumption would vary widely, because I might be rich and I still go to McDonald's. I can be rich and I go to a 5-star hotel to have my dinner, right? So you have wider options, and that's why the amount that you pay for your consumption might vary very widely as your income increases. So this picture is homoskedastic. This picture is heteroskedastic. Okay. All right, so I just gave you the graphs to get you an idea about what I'm talking about. Okay, so if I have heteroskedasticity, what's going to happen to the blue estimator? The blue estimator will still be unbiased. The blue estimator will still be consistent. However, it will be inefficient. So I don't have any problem with these. My problem is related to the variance, because it's all about, it's a heteroskedasticity is all about the variance, right? So if you can see here, I didn't mention anything about the point or the expectation of the variable, which is the center here. All what I was talking about is the variation around the center. So there is no problem about the unbiasedness. There is no problem about consistency. There is a problem about efficiency, because we will no longer have the minimum variance or efficient estimator. If I have inefficient estimator, I want you to imagine how this would affect the t-statistic, because again, the t-statistic, I have the upper part is unaffected, right? If this is J, but the lower part, which is the standard error, which is the standard error of the estimator, is going to be affected. And if this is high, right, high variance, low t, okay? So if the t-statistic is affected, the p-value is affected, the confidence interval is affected, the f-test is affected, they are all going to be affected. You will end up by wrong tests, misleading results. So anytime you have heteroskedasticity problem, or you have data set, right? You got your data set, you need to figure out, okay, is this data set homoskedastic, heteroskedastic? How can I find this out? So before I proceed, I just want to make sure that we are all on the same page. So when you look at your model, let me have like a simple model. Okay, I don't have any issues about the expectation because the center is going to stay the center. The center of, or the conditional mean of yi, just take the expectation operator here. So it's going to be again beta naught plus beta 1 xi plus 0, because remember I said before that the expectation, and this is an OLS assumption, given xi is equal to 0. Okay, so I will end up by, let me remove this last part. So this 0, I don't need it. So I'm going to end with this. What about the variance? Because this is our topic today, which is the heteroskedasticity. What about the variance of rent given income? Okay, so I'm going to take this variance throughout my equation, and I want you to know that if I take the variance of a constant given income, it's gonna be 0 because the constant does not vary. What about the variance of beta 1 given xi? Again, variance of a constant does not move. The variance of xi given xi, it's not random, so it's 0. Then I'm going to be left with the last part, which is equal to the variance of ui given xi. And based on the OLS assumption, I said that there is no connection between the error and the x. So I can always write it as like, okay, it's ui. Okay, and what is the variance of ui? The variance of ui is simply, you can open the ui up, right? So the variance of ui is equal to the sum of ui hat minus the average of ui hat bar squared over n minus k minus 1. And if you have studied our lecture of last week, this part, which is the u bar, I always get confused which one should I write first, the hat or the bar. So let me just make it with the hat first, because this is what's supposed to be. Okay, u hat bar, okay, which is the average. It's like the average of anything. It's ui from I equal 1 to n over the sample size, right? And as per our OLS assumption number 1, this is actually equal to 0 because the conditional mean is equal to the mean of the error term, which is the ui hat bar, and it's equal to 0. So you can actually think about this part is gone because this is actually 0. And you can say that, okay, I can write the variance of ui as simply the sum of ui hat square, right, over n minus k minus 1. And if you have studied your notes from last week, the upper part has a name. You guys remember what's the name of the upper part? Anyone? What's the name of the upper part? It has an I equal 1 to n. Remember, all the summation signs has I equal 1 to n. Anyone, what's the name of the upper part? It's the sum of the squared residuals. So if you need to check your notes, SSR over n minus k minus 1. Okay, so that means that
Sorry, you said it was the sum over what?
It's the sum of squared errors or residuals.
Okay.
Yeah. Mm-hmm. And you can actually call it the sum of the square, the mistakes, the sum of the squared errors, but I'm going to follow as SSR. Okay, which is always constant, and it's taking like notation sigma square. Okay, so sigma square is the notation taken for the variance of, remember, everything here I'm talking about is about this, the variance of UI, the error term. So when you see this, doesn't have any sub I, so it's constant. So the OLS assumes homoskedasticity. So this one is constant or homoskedasticity. And what we're doing is we're simply dropping this assumption and see how our model performs. Okay, so what are the reasons for heteroskedasticity? There are actually two important reasons for heteroskedasticity. Okay, so and remember, this is unequal variance. Right? There are actually multiple factors, but let me focus on the two things that we see a lot. If I do have outliers, so if I have a model that I have here consumption, this is consumption, and income, and this is the data set here saying that there is a positive relationship. However, I have one point out there. This is an outlier. Okay, so the presence of outlier, when I come here and try to find what is the amount of average errors in the model, an error would be the distance between each dot and the regression line. Remember, the dots here are the actual data, and the line here is the estimated. So you can think of the actual data, which is y, and the estimated is yi hat. So the distance between the dot and the line would give you the amount of errors. So if I have a dot which is all the way far here, then it would give me like an amount of errors which is huge, and would give me like a misleading result that, or a misleading impression that, okay, I do have this observation that is far away from my regression line, and this means that I have a large amount of errors. So if you take this amount of errors, suppose that this one is UI, suppose this is the errors of person number 10, and this is the error of person number 1, this is the error of person number 2, and so on. Like each and every dot that you see here would be related to the distance between the dot and the actual regression, and would give you the amount of error. If you include this large amount of error of person number 10, then it would give you a wrong information telling you that you have a large variation in your data set. Okay, so this is like, especially this would happen if you have a small sample size. If I have a sample size of 10 people and I do have one of the 10 has a data point which is far away from the range of observation, then the heteroskedasticity problem would be like very apparent in my model. So I want to make sure that anytime I have a data set, I'm graphing it, I'm making sure that all the dots seem kind of normal. There is nothing abnormal in my data set. There is nothing that is weird and way out of the range of observations. Then, oh, sorry, why I'm saying 4? It's okay, 2. So another problem, which is misspecification error. And I want to actually to make sure that you get this connection, because as I said, our topic has heteroskedasticity, multicollinearity, and misspecification error. There is a connection here between these two. If I have a misspecification error, I might lead to heteroskedasticity. So you might have a nice and an unproblematic model, which is homoskedastic and everything is nice, but because of a problem that you made in your model, you have created a heteroskedasticity problem. So I'm just going to briefly talk about this point because we are going to spend so much time on it anyways. So what is a misspecification? So suppose that I do have a model which is demand for good X is equal to beta naught plus beta 1. The price of X, okay, plus beta 2. Let me think about one of the variables I want to include. Let's say advertisements on the product, okay? And then you have the amount of errors. And this is I because it moves on all the goods that you have. And then suppose that this is called the correct model. And suppose that you decided to estimate this model. And this model is beta naught plus beta 1 price. And that's it, you stop here. And then VI, which is the error term of model number 2. So this is the correct model, which is number 1. And this is the wrong model in which you forgot an important variable, which is what is the amount of advertisement on this product, because the more the people are aware of this product, definitely it would affect the sales of the product. So when it comes here, okay, you forgot this variable in model 2, but it's actually included in here. So here it would have like, okay, this one would be equal to beta 2, the variable which is advertisement plus the amount of error. So you forgot it in model 2, but it's actually included in the error term. And the price and the variable that you forgot are connected, right? The more advertisements, the more the people are aware of the product, the more the demand, the higher the price. So there is an indirect link between the two. So you have, because you have forgotten an important variable, this important variable appears in the error term and making the error term connected with the included variable, which is the price. So you have created a heteroskedasticity problem because of omitting an important variable. So how can you avoid that? So by looking here, I can avoid this outlier by graphing my data set, checking that I don't have any problem in terms of like a data point outside the range of observation. And for point number 2, which is the misspecification error, how can I avoid that? I need to study my model. I need to make sure that, okay, demand of a certain good depends on price, advertisement, consumer taste, price of substitutes, price of complementary, population, all the things that you have studied in your microeconomics. Okay, so before fitting any model, you have to make sure that you study the model very well so that you're not missing or you're not running into a problem that you can easily, or econometric problem that you can easily avoid. Okay, so any question? You guys are silent. No questions? You're fine? So let me ask you a question. So when we say heteroskedasticity, is it about the expectation of yi, or it's about the variation of yi? Can who's going to answer this question? How about Parth? Hello? Parth, can you answer this question? Okay, how about Othman? Can you answer this question?
I'm trying to do it right now.
Would
You
it,
don't have to do anything.
would it be the second choice?
Huh?
Would it be the second choice?
Yeah, so heteroskedasticity is all about the variation, right? So it's all about the variance. It's not, has nothing to do with the expectation, right? The center of observation is going to stay the center. We just need to ensure that the variation of yi is constant. And if it is not constant, then I have to figure out how I'm going to deal with it, as I'm going to show you. Guys, I hope that you're logging into Zoom and attending the lecture, okay? I do have like my two boys, I have two boys, and they are both Rutgers students. And I can see what they are doing, okay? They open the lecture and they go do something else, unfortunately. So I hope you're not doing the same, because econometrics is not something that I can...
I wouldn't understand this if I did that.
This is a lot, miss. I can't even lie. Like,
Maybe with some other classes I've done that, but not this one.
With
Yeah.
econometrics again, because I
No,
have...
I can't. It's confusing as is.
Exactly. My older one, he's like a senior this year. He's gonna graduate in May. He's like, okay, he has like this iPhone, and then the professor is talking, and he's doing something else on Instagram. So like, you're crazy. And my younger one, he's like freshman this year, so he's taking it more seriously. He was taking it more serious at the beginning, like the first week, and then he was like kind of relaxed. Oh, okay, I understand what college is about. No, no.
Yeah, we've all been there though.
So I've seen my boys, and they said, okay, I hope my students are not doing with me the same thing, because it's not about me. I really don't care, because I'm recording anyways. If you guys are not here, I'm recording anyways, and I'm posting it anyways. But it's all about you, because with econometrics, you won't be able to understand. And
No.
many of the things I mentioned during the class are not available in your textbook. So I would like take things from here, things from another textbook to enrich like the examples and so on. So anyways, stop me if you have any question, because otherwise I will try to figure out where are you. Okay, so far Parth is not here. Dan, are you here? Okay. Okay. Anyways, who's this? Dan?
Yeah.
Okay. So the next question is yours. Okay, I'm gonna ask you in a few minutes. I'm not gonna tell you when. I'm gonna ask you in a few minutes. All right, so let's talk about the detection. So it's very important, like knowing the problem is nice, but we need to detect the problem, right? So how to detect heteroskedasticity? Let me write in a clean page. So okay. So there are easy things to do, and I already mentioned, okay? So if you don't have any empirical information, like you're doing a research and that is kind of a brand new, and you're using a model that is your contribution to the literature, and you don't have any information about this model, whether it's heteroskedastic or homoskedastic, then you just simply graph it, okay? So a graphical representation or graphical method, it's like an easy thing to do. What you need to do is going to take each and every X you have, right? And you graph it. So Louis, can you mute your mic, please?
Sorry.
Yeah, that's okay. Okay, so what you need to do is you're going to graph the variance of yi on x1, and then you're going to repeat the variance of yi on x2, and then the variance of yi keep going on xk. So if I have k x's, I'm going to have k graphs. And some people would do the variance of yi or the variance of ui because they are the same. If you go back here to one of my slides, I'm gonna try to find it. Yes, here. So the variance of ui conditioned on x, you end up by being the variance of the error term. So it's either or. You can either use the variance of y or the variance of u. So you take the variance on the y-axis. So here I usually use the variance of u on x1, okay? And then I'm gonna repeat it with x2. And I'm gonna repeat it with xk and so on. And every time I have the variance of ui. And when you say, okay, what do you mean by the variance of ui? You can just simply say, I'm gonna use ui hat squared as an estimator for the variation, right? Because this is going to be the distance between each yi minus the estimation, which is yi hat, and it's squared, and it's gonna move for each observation. So you can actually remove this and say, okay, it's going to be ui hat squared, okay? ui hat squared, ui hat squared. And you can have different options, okay? If I get something like this, what does that say? Basically, I can take it into a certain range. It shows me kind of as x increases, the variation of the error term is kind of constant within a certain range. So the variation here doesn't seem to be significantly moving, right? It's between these two lines. It's between certain range. Of course, it's not, if it is too wide, then it might be heteroskedasticity. But if it is moving, as you can see, it doesn't change much, then this would be like homoskedastic by just looking. If it is something like it gets smaller and then gets wider and wider and wider, I can put it into a range like that, it opens like that, then it's heteroskedastic. I can have also different possibilities. You can have it like this, inverted U shape, right? So you have it like into this shape, or you can have it like a U shape, heteroskedasticity. Anything that is not constant, then it's heteroskedasticity, okay? So, of course, looking at the graph, like for me, when I just use my eyes as a test, I always need to back it up with a test, statistical test. So you can always do the graph, but you can't just 100% depend on it, because let's say with the first one, yes, I can see it doesn't like move significantly, but it might be there might be a movement that is significant that I cannot see it with my eyes. So what you need to do is you do the second test, which is a regression. So a regression is, again, doing the same thing. I'm going to regress what I had on the graph. So I'm going to regress or create a model of how ui hat square is affected by x1, x2, x3, each one in a turn. So let's say it's going to be like beta naught plus beta 1 x1, and I'm going to have an error term for this regression. Let me call it xi, because I don't have x1, x2 here. Okay, so it's just on x. So you're going to have this regression, and out of this regression, you would get an r square. So you get an r square, which is the explained sum squared over the total sum squared. To what extent the variation in the x is explaining variation in the error term. And I need to have a certain benchmark, and your benchmark would be if this r square is greater or equal to 0.8, which is 80%, then I'm going to say, like this is or 80% explanation. Then I'm going to say I have heteroskedasticity. Okay, so a regression, how can I do that? Like I need actually, before I come to the step, I need actually to have a certain model. So I have a model which is, okay, yi is equal to beta naught plus beta 1 xi plus ui. And then I got the ui hat, which is the beta hat naught plus beta hat 1 xi. And then the difference between these two is the ui hat, and then I'm squaring it and taking into a regression to with the x in order to check if there is any connection. And I want you to note that actually I might have a bigger model. So I might have not only 1x, I might have a model like this, beta 1 x1 plus beta 2 x2, and I might have beta 3 x3 all the way up to beta k xk plus ui. And then I'm gonna have an estimation, beta 2 x2. And then whatever I'm doing here on x1, I'm gonna be repeating it here, another regression for x. So this is x2i, okay? And this is the error term of this regression. And again, you check the R square of this regression. It might be the case I have heteroskedasticity with x1, but I don't have a heteroskedasticity with x2. So if I have x1 and x2, then this would be like x1i, and this is the regression of x2i. Okay? The third way of detecting heteroskedasticity is the nature of the problem. What is the nature of the problem? So anything that is related to group of people, group of countries in a certain point in time, group of students in a certain semester, and so on, anything that is cross-section. So cross-section is group of, let's say, people in 1 year or 1 month or whatever. So it's a cross-section group of countries, governments, individuals, students, anything. Usually we are not the same, right? So we have different educational backgrounds, we have different age, we have different salaries, we have different experiences. So if you are talking about a cross-sectional model, then just most likely heteroskedastic. Most likely, okay? However, if you are talking about a model which is time series, which is one variable over time, it's the same variable, right? Over time. So most likely this variable will not be so different, or the variation of this variable will not be so different over time. So if I'm talking about inflation over the period from 1980 to 2000, for example, in USA, this is an example of a time series. It's the same variable. So the variation of the variable around its mean supposed to be not very significant as compared to the variation of the salary of different individuals in a certain point in time. So most likely, if the nature of the problem related to cross-sectional model, then most likely it's a heteroskedastic. Time series, most likely it's homoskedastic. But again, I'm saying most likely, so we have to test, okay? Which is the next point that we're going to talk about, which is actually the most important point, which is performing a formal test. One of the things to mention about the nature of the problem is for people who are doing research, let's say on family budgeting, which is how consumption of a certain family is affected by income. And this is called family budgeting models. If people working with family budgeting models, they already know that there is heteroskedasticity because different families have different consumption behavior. So that those people, they don't have to do the test because there are already multiple papers on family budgeting, and everyone knows that it's heteroskedastic. And I'm giving you just an example. So if you're doing a research in a certain field or a certain area that it has been already known that it's heteroskedastic, you don't have to perform the research. I mean, like, you don't have to perform the test. You can just refer in your paper or in your project that based on previous research. And that's why the literature review in a project is important, because you need to go over what people have done and see what is your contribution, right? So if people have already done it, you don't have to repeat. It's just you refer to them. So you refer and say, okay, I'm assuming I have heteroskedasticity because based on previous research papers, there is heteroskedasticity. All right. Number four is the test, formal test. And this is what we usually depend on. So a formal test, there are different tests. So this is formal test. So there are like multiple tests that you can use. The first one is called the Bruce-Pageant test. And this is actually the last name of person number one, the last name of person number two, and they have created a heteroskedasticity test. Again, the test is all connected to the same story I'm talking about, the variation of the error term versus the axis in the model, okay? So the second test, which is called the, I don't know which one should I mention first, okay. The LM test, okay, which is called the Lagrange multiplier test. And I'm going to talk about it. And there is also the White test. And there is the updated White or advanced White. I can't remember the name. It's alternative, okay. It's not updated, it's not augmented, it's alternative White test. Okay, so these are 4 tests that you can use in order to determine whether you have heteroskedasticity or not in the model. And this is what we do. Like, you guys are about to graduate and you're probably going to have a job. And if you're working in a research department and you're doing quantitative analysis, you're not going to depend on a graph and say you have heteroskedasticity or not. You're not going just to depend on the R-square, but you need actually to perform a formal test. And the idea is, again, very, very simple. It's all about the connection between what you see on this graph. Error term squared, each x, okay? So we're going to do a test, and anytime you see the word test, you need to see a null and an alternative hypothesis. So I'm gonna start, this is my favorite one, okay? So it's my favorite because it's easy, straightforward, and the most commonly used test. So the first one, you know what? I'm gonna call it the BP test. Okay, from now on, we're gonna call this one the BP test. Okay, so the BP test has this null hypothesis, which is saying that the variance of the error term given x1, x2, xk is equal to sigma square or constant, okay, constant. And actually this one by default in theta it's 0, okay? And the alternative is that the variance of ui given x1, x2, all the way to xk is not constant, okay? So as you can see, this null is about homoskedasticity. This alternative is heteroskedasticity. Okay, so how can I do this test? So in order to do this test, you're going to do a certain regression. And the regression is similar to the one I mentioned in the previous slide, which is basically you're going to regress So you're going to regress or estimate, okay, this model. Ui hat square, and you already know how we got the error terms, the error term from yi minus yi hat, and you take it and then you square it, and then you use it as your dependent variable on this regression. I'm going to use delta instead of beta, it doesn't matter, right? Just different notation. And then delta 1 x1i, and then delta 2 x2i plus delta k x ki plus a certain error term for this regression. My null hypothesis is simply saying that there is no connection between the x's in the model, or the regressors in the model, and the variance of the error term. So it would be like this. There is no connection, so this one has to be 0, and this one has to be 0, and this one too. So this one is telling me no connection, homoskedastic. And then the alternative is saying, no, there is a significant connection, because this one is not equal to 0, and or this one is not equal to 0, and or is not equal to 0. You keep going, okay? And or delta k is not equal to 0. Or you can simply say, actually you can, like, you make your life easy and say, instead of all this, one or more of the above restrictions does not hold. Like, sometimes you can actually make your life easier, and instead of writing this whole alternative hypothesis, you can say one of the above, which I am referring to the null. One of the above restrictions does not hold, which means that one or more of the deltas is not equal to 0. Okay, so anytime I have a test that has multiple coefficients, do you remember what's the name of the test? Is it a T, P, F, R? What is the name of the test if I'm testing multiple coefficients?
R.
R is about the explanation of the model, right? So
F test, right?
exactly, the F test. So we did that last week, where we're doing, anytime I have more than one coefficient to be tested, then I'm talking about the F test. So the F test is going to take the R square of this regression, right? So it's going to be like R square of the model of U divided by 1 minus R square of this model, which is U, and adjusted with degrees of freedom, how many parameters I have. K, let's say I have K coefficients under the null, and here I have sample size minus the number of coefficients minus 1 for the intercept. So this is, you don't have to memorize it, of course, but you just know how it's computed in this data. So you get the R square of this regression, and it's computed based on this formula here. And as you can tell, this has an F distribution with K, or how many, you actually count how many coefficients to be tested here. If I have K coefficients, then I have K degrees of freedom for the numerator, and N minus K minus 1 for the denominator. And then, as I mentioned last time, F statistic has a distribution on one side. It's all made of squares, so it doesn't have a negative part. Okay, so the F statistic, we need to refer to the table to find out, okay, how many restrictions, I mean, like, refer to the table to get the critical value, right? So critical value would be here. So suppose that I have, for example, F of anything. Okay, suppose I have 3 x's, okay? And large sample size, infinity. So if you go back to, where is the table of the F statistic? I think it was it this one? Yes, this is the 5%. So suppose that I have 3 X's. What I need to do is I need to find number 3. Let me use another color. So if I have 3 X's, then I'm going to use number 3. And then I need to figure out, okay, what is my sample size? If my sample size is more than what I see here, which is going to be the case, which is 120. You see here, I have 120 is the last row here. So most of the time we're working with more than 120, and that's why I take the approximation, which is the infinity. Okay, so based on 3 coefficients, 1, 2, 3, I'm going to take, so this is my critical value for F3 infinity. So we're gonna call it F3 infinity. If I, and this is just an example, I made any number, right? I said, what about if I have 3 X's? If I have 4 X's, then this is my critical value. If I have just 1 X, then I'm going to have, this is my critical value, and so on. So the F, let's say the F3 is 2.6. So if I have only 3 X's, then this is gonna be 2.6 as a critical value. Remember, if we are here in the rejection region, right, then I'm going to reject the null of homoskedasticity and say I have heteroskedasticity. So if the F that you calculate from the formula you see here is greater, okay, if it's greater than 2.6, then you are in the rejection region. So reject null. And remember, the null is saying homoskedasticity. So you're going to conclude I have heteroskedasticity. So the model is heteroskedastic. And the opposite is true. If the F I calculate from this formula is less than 2.6, and again, I'm just making the assumption that I only have 3 X's, so the delta stop here. Then I'm going to accept the null and say, okay, I have homoskedastic model. Okay. What about the other test? Do you have any question about the BP test? I'm going to show you in Stata. Actually, in Stata, it's very easy. You just type one command and then you get the BP test, and then all what you need to do is to analyze it. So how can you find out the critical value? And once you get the critical value, how can you analyze whether it's a hetero or homoskedastic? The other test, which is the LM test, the LM test is actually, it makes use of the same regression. So number 2, the LM test, which is called the Lagrange multiplier test. So it has this formula. It simply takes your sample size, multiplies it times the R square that you get from the regression of UI hat square. That's it. So suppose that I'm just making any like any numbers, for example. Suppose I got this R square from this regression to be equal to 0.10, which is 10%. In other words, the group of X's explain only 10% of the variation in the error, in the variance of the error term. So suppose I have N is equal to anything. Let me make any number. Okay, 100 people. Okay, so the LM, it's going to be this 100 times, right? So it's going to be equal to 10. So the LM is equal to 10. How can I analyze that? So the LM, I have to have a critical value. Again, every time I'm doing a test, I do have a formula from which I get the calculated test, and then I compare it with the table, right? Or the critical value table. So I have to know whether this, I have to know the distribution of this test. So this test, as you can see, it's made out of squares. So it's made out of squares, and I want you to check chapter 3, because in chapter 3 is telling you when I'm going to use which distribution. Of course, the more that you practice with me in this course, the more that you would understand each test is related to which table. So the LM test has a chi-square distribution. The chi-square is used whenever I'm talking about a test that has all squares. It has a distribution with k degrees of freedom. This is k. And this is how many x's I have under the test. So if I have a model in which, okay, ui hat is equal to alpha 0, which is the intercept, I'm gonna call it alpha. And remember, I'm gonna use different, it doesn't have to be beta all the time. I'm just gonna make anything. So alpha node, alpha 1, x1 plus alpha 2, x2. And I did this regression, and I was able to get the R square of this regression. We call it R square ui hat squared, because this is squared here, okay? My null hypothesis, again, it's gonna be the same as the previous test. This coefficient is equal to 0, and this coefficient is equal to 0. So when it comes here, how many restrictions I have 2 coefficients to be tested. So here the k is equal to 2. So I have to go to the chi-square table, right? And check the 2 degrees of freedom. Every time I'm changing this k, depending on how many coefficients I'm testing. I have the chi-square table somewhere here. I just took a picture. Okay. Is this this is not the chi-square, wait. I had the chi-square somewhere. No, I don't. This is the, oh, right here. So I want you to check this chi-square in page 724, table 3, the chi-square table. How can I use this? It has like, it's making our life easy. We have 3 columns, 10%, 5%, 1% for the significance level. And remember the F statistic, we have 3 pages, not 3 columns. It's more detailed. So all what I need to do is I need to look for the critical value for the chi-square, right, with 2 degrees of freedom, assuming that I have only 2 x's. So it's up to you to choose which significance level. By default, I use 5%, or most of the people, they use 5%. So if it is in an exam and I'm telling you 10%, then you use this one. If I'm not saying anything, you choose whatever you like, okay? And you base your analysis on your choice of the significance level. So anyways, my degrees of freedom are 2. If I'm using the 5%, then this is 599, my critical value, okay? If you're using the 1%, then 9.21 is your critical value. So, okay. So your graph, again, similar to the F, 5.99 under the critical value, the critical value under the 5%, again, rejection region. You do the same thing. So if the again, if the LM test that you get is greater than 5.99, so whatever you compute here is greater than 5.99, you're going to reject the null, that these coefficients are equal to 0, and you're going to, or reject the null And remember, the null is saying homoskedasticity. And when you reject the null, you're going to conclude that the model is heteroskedastic. Okay. Any question? Okay. There are actually the white test and there is the alternative white test. So let me go over these. And then I'm going to show you this data and then hopefully we do application. And I don't think I would have time to cover whatever I wanted. We'll see. Okay, so the white test, what is this? So number 3. So white test, again, it's the same idea. However, the white test allows for a connection between the x's and the error term that is allowing for some non-linearity. So it would be like this. Okay, ui hat is equal to delta naught plus delta 1 x1i plus delta 2 x2i plus delta 3 x3i. And then it allows for non-linearity, in other words, square of quadratic model. So delta 2, no, it's actually delta 4 x1i squared plus delta 5 x2i squared plus delta 6 x3i squared. And then it adds interaction term or multiplication, or how about the effect of x1 and x2 simultaneously at the same time? So it would add another 3 terms, delta 7 x1i multiplied times x2i plus delta 8 x1i x3i plus all the possibilities. As you can imagine, it's kind of a very broad test which allows for possible nonlinearity, possible interaction or multiplication between the variables in the model. Here I have just 3. I just made an example of 3, but you can have it like as wide for 7 x's or more. Okay, and then x2i, x3i plus vi, which is the error term of this model. As you might expect, if I'm trying to check whether these x's, all these x's and the different versions of these x's, the quadratic interaction, whatever, are related with the error term, remember this is squared here, then your null hypothesis would be like this. Starting from delta 1, whether delta 1 is equal to delta 2 is equal to delta 9 equal to 0. And this is again homoskedastic. Alternative, whether, let me write it in a different way instead of writing not equal to 0 and or and so on. And we're going to say one of the above restrictions does not hold. Just a different way of writing the alternative. Okay. As you can imagine, again, this is a chi-square test. Again, you're going to go to the chi-square table, get the results, and I mean, like, get the critical value and so on. One of, like, actually, you're going to be using the same formula here, but the R square is going to be different, right? So it's just the same formula here. But the R square is different based on the different tests. The alternative white test, it's say alternative because, as you can imagine, I have here 9 coefficients. If I have 3 x's, imagine you have 4 x's, imagine you have 5, 6, 7, you will keep on estimating multiple coefficients, and the more and more coefficients you estimate, you keep losing degrees of freedom. Degrees of freedom are here, n minus k minus 1. The more x's I have, the higher the k, the less the degrees of freedom and the accuracy in the model, especially if you have a small sample size. So the alternative white test would be, okay, let's combine these into like into their wise. So it would be like this. So number 4, the alternative the alternative y test would be, okay, we're going to combine this into alpha 0 plus alpha 1 yi hat plus alpha 2 yi hat square plus vi. So it's alternative because if you open this and you open this, you would recover the previous test, which is the y test. So the alternative test is simply trying to minimize the number of coefficients to be tested so that we're not running out of degrees of freedom. So the null hypothesis would be, okay, alpha 1 is equal to alpha 2 is equal to 0. Again, homoskedastic. And then alpha 1 is not equal to 0 and or alpha 2 is not equal to 0, heteroskedastic. And again, you get the R square and you plug it into the same formula here, and then you analyze it based on the chi-square table. Okay? All right, so this is all about the heteroskedasticity part. What I'm gonna do is I just wanna show it to you in Stata because in Stata we will, I'm going to share with you my computer. So can you see now my Stata do file?
Yeah.
Okay. So this is, okay, the first part, I'm not going to talk about it because you have it in like as a video in on Sakai. Let me show it to you here. So in Sakai, if you go up here, where is it? Yes, here. Heteroskedasticity tests using simulated data. So in here, I'm actually talking about the do file that I'm opening, which is the upper part of it. What I'm gonna do now is I'm going to talk about the lower part of it. So I want you to watch this and make sure to take notes because this actually complements our today's lecture. Okay, which is heteroskedasticity test using simulated data. Simulated data is just a data that you just create. It's not an actual data. So what I'm gonna do now is show you how we can do the test with the actual data. So on my do file here, I do have the upper part of the simulated data. This is the starting part. This is what you have on the video, okay? And then I'm going to start here where it says repeat using actual data. So the data I'm using is the relationship between a model that is about the relationship between income, education, years of education, and job experience, how job experience would affect your income, how education would affect your income. And I already got the data here. So when you do the regress command, it's just a simple command that we did last time. You get the coefficients. Remember, and I'm not going to repeat this every time, anytime you have a model like that in your homework, let's say that you will have to submit towards the end of this week, you have to analyze each and every column that you see. Okay, so here, for example, each year of education would increase income by approximately $1.93, and the unit of measurement of income is in thousands. Okay, so this number would be 1.93 multiplied times 1,000, right? So we give you the impact of education on income. And remember, anytime you're analyzing a coefficient, you have to mention that holding job experience constant. A 1 year increase in job experience would increase income by like approximately $0.65 or 65 cents. And again, you multiply this times the unit of measurement of income. Okay. As you can see, the coefficients are statistically significant. You're passing the 196 critical value under the 5%, or you can actually look here and say statistically significant because very low probability of having a zero coefficient and so on. So I'm not going to repeat it, like whatever I'm saying is a repetition of last week interpretation of a model. So what we're going to do today is the BP test. Okay, where is it? I'm sorry, I keep going up and down. Okay, the BP test is a command that you write under the regress command. So state command and then het test, heteroskedasticity test. So estimate heteroskedasticity test. So when you do it this way, okay, this is what you get. You get the results telling you that the null hypothesis is about constant variance. The variables that you're testing is fitted values of income. So you're actually getting the Y, which is the dependent variable, or the Y hat, this is the variable that you're testing. The result that you see here is like, your life is easy because you don't have to go to the table, because whenever you see the P or the probability of the test, it's easy to look here and say, okay, there is a 72.38% probability that I have a true null, which is a constant variance. This is a big number, right? 72.38 exceeds the 5% significance level. So you would say, okay, 72.38% probability of a constant variance is a huge number compared with the 5% significance level. Accordingly, what you're gonna say is, I have a homoskedastic model because I have a huge probability that this is true. As you can see, we have different versions of the test. This one here, right? When you see, sorry, I keep going. So this one here doesn't have IID. This one is saying that you don't have IID assumption, independent, identically distributed assumption. However, if you want to add IID, you can add IID to the test and repeat. Just you check whether it makes any difference. And all it depends on the question. If you have a question and I'm telling you to use IID or not, then you would adjust your test based on the question. So when you look here, it actually doesn't make a big difference because still the probability is huge, okay? So there is a 65.57% probability that the null is true. In other words, the 65.57 is greater than the 5% significance level. It's greater actually than the 10%, all right, conventional levels. So you're actually saying that there is a high probability of homoskedasticity in the model. Okay. You might also do a different version of the model. So what if I'm asking you to do it on the axes, like education and job experience? You can actually do it on job experience only, on education only, or on both. Or if you do it like what we did, actually like here and there, it's on the combination of both, which is the YI hat. And that's why when we say fitted value, let's see here, fitted means the dependent variable. And the dependent variable is known to be like the linear combination of the independent variables, right? This is the dependent variable. When I take income hat and I perform my test on income hat, it's simply the linear combination of beta naught, beta 1 education, beta 2 job experience. What if you want to do it specifically on the axis? Does it make any difference? So you go back here and you check. As you can see, the variables under the test are education and job experience. Testing are constant variance. See this number. Okay, so this number is 3.47%. Is this number is big compared to 5%? No. So there is a small probability, right? Because it's a smaller than 0.05 or 5%. So there is a small probability that the null is true. There is a small probability of constant variance. In other words, we are actually in the acceptance region. We are failing to reject the null. And we're saying we have, right, you fail to reject this one. So you basically say you have heteroskedasticity, right? So there is a small probability, right, that this is true. So you basically say you have, wait, I got confused. There is a small probability that there is a constant variance, yes. So you basically have heteroskedasticity. Okay. So any questions before I move on? Any questions? Okay. Next, there is also an like the IM test. The IM test is for the white test. And again, it has to be written right under the regress command. So if you do it this way, right? This test would give you 3 tests together, okay? And I'm writing it here. I'm going to be posting this do file for you. So this test is about a null hypothesis that says homoskedasticity, symmetry, and kurtosis, which all about the distribution of your model. The alternative is if I don't have homoskedasticity, I have heteroskedasticity, symmetry. If I don't have symmetry, I have a model that is skewed to the left, skewed to the right. I like this is something else, and or more details about what type of symmetry we're talking about, and then kurtosis. If we reject, then we have a non-normal kurtosis. Okay. So again, you basically look at the p-value. It's the easiest way to analyze any test. So here I have 11% probability, which exceeds the 5%, 11% probability of homoskedasticity. Okay, so the model is homoskedastic. I have a 30% probability of symmetry. Okay, so the model is symmetric. And then I have a 32.26% probability that the model has non-normal kurtosis. Okay, so based on the IM test, and I have the conclusion here written for you, based on the test, you have heteroskedasticity, right? You have skewness and non-normal kurtosis. Okay. If you're not sure if you understand the skewness and kurtosis, you can go to chapter 2. All right. Let me make sure that I repeat the heteroskedasticity because I felt like I was confused with the third one. So I just want to make sure that you can read them correctly. Okay. Remember here, every time you're talking about the null hypothesis, here constant variance or homoskedastic. Okay. Now, this exceeds the 5% high probability of constant variance, then homoskedastic. Okay, so there is a high probability, 72.38% probability, which exceeds the 5, then we have homoskedastic. Okay, and then 65.57% probability of constant variance, then homoskedastic. Okay, now here there is a very low probability of constant variance. Then when I do it in the x's, very low, I'm talking about the 5%, very low probability of constant variance, then I have heteroskedasticity in when I perform the test on specific x's in the model. I wanted to also understand something, that here I'm referring to the 5% as my benchmark, right? What if I'm referring to the 1%? This number exceeds the 1%. So under the 1% significance level, I can say that this number is big because it's 3.47 exceeds the 1%. So under the 1%, I have homoskedastic. So I might have a question, let's say in the exam, and I don't tell you which significance level you can use. And I have different answers because different students are using different significance levels. That's perfectly fine, okay? So you have to tell me in your writing, okay, I'm using this specific significance level and I'm basing my analysis on this specific significance level. Because this is one of the things that, okay, it's bigger than 1, but less than 5. So bigger than 1 So it's high probability of constant variance using the 1% significance level, then I can conclude I have homoskedastic. But if I base my analysis on the 5%, then I have a low probability of constant variance, I have heteroskedasticity. So this is one of the cases that it can go hetero or homoskedastic based on which significance level you're using. In real life, in practice, like if you're doing this as a research or a project, to be on the safe side, something like that, you would consider it as heteroskedastic and use the and deal with the model as being heteroskedastic. So if I have heteroskedastic, how can I correct the model? So whenever you have heteroskedasticity, you have to estimate the model using something called a robust standard error. So I have to adjust the standard errors of the coefficients to meet the fact that I have a correlation between the axis and the error term. Okay, so let me do it here. So let me take this model and add robust standard error, which is R. So if you add the R here, this would change the standard error from the regular standard error that you see it here. This is a regular standard error. See, it's called standard error. So this is the normal standard error. But based on let's say the results of the test, and suppose that you felt like, okay, let me be on the safe side and use the robust standard error, because the robust standard error work anyway, whether I do have a homoskedastic or heteroskedastic model. So suppose that you decided to use the robust standard error. So you just add, either you type robust or type R. State would understand. What you get here is the robust standard error. The robust standard error is an adjustment to the regular standard error, allowing for the possibility of correlation between the axis in the model and the error term of the model. I want you to notice that the coefficients themselves do not change. So when you go up here, this is 1933, 0.64, -7. They do stay the same, 1933. So the robust command, or option, I should say option, does not change the coefficients. It does only change the standard error, and accordingly will change the T, will change the P, will change the confidence interval, because they are all connected with the standard error. Okay, so let me show you how the formula of this robust standard error. Okay, so that you're we kind of completely close this part. So let me go back to my iPad, and so as I said, which is the very last part, how to deal with heteroskedasticity. So what we're gonna do is we use a different standard error, which is called robust standard error. Okay, the robust standard error, it allows for a correlation between ui and xi that is not equal to 0. So it kind of drops the assumption of OLS that I don't have any connection between the two. So to let you know that our homoskedastic variance is equation is like this. So I'm not sure whether I give you the whole derivation. Okay, so we know that beta hat is equal to the sum of xi, yi, and this is a simple way of writing it, xi squared. And I want you to imagine that this xi is equal to xi minus x bar, and this yi is equal to yi minus y bar. Just I'm writing it in a simple way, covariance over variance. Okay, so what is the variance of beta? it's equal to the variance of this whole thing. Okay, and then it's equal to, you take this outside the variance operator, so it's going to be equal to xi squared, the variance of ui over the sum of xi squared whole squared. Okay, so in homoskedastic case, this variance is constant, right? We said this one is constant, is equal to sigma squared. And I can always like remove one of these with one of these, right? So I can simply say that, okay, I can write the variance of beta hat as equal to sigma squared over the sum of xi squared. So this is like your homoskedastic standard error. And this is the one that is computed by default in Stata. If you perform the BP test and you realize, okay, or the IM or the LM test, and you realize, okay, I do have a heteroskedastic model, I need to use the robust standard error, then this part is no more constant, right? So this part is going to be correlated with the X. And we can write it this way. So let me have this here. Okay, this is, okay. So in heteroskedastic case, this variance is not constant. The variance of ui is not constant. It's equal to the expectation of ui squared. And I want you to check the chapter 2 and you see this derivation. So in heteroskedasticity, if I have the variance of beta hat, it's not constant. It's going to be equal to xi squared, expectation of ui squared over the sum of xi squared whole squared. And your final equation would be equal to the sum of xi squared ui squared over the sum of xi squared whole squared. Now, this is called the robust standard error. It allows for a correlation between the X and the error term. It's not anymore constant. So anytime I have proved based on the BP test that I do have heteroskedasticity, then I need to use this robust standard error using this equation so that I can allow for this type of correlation. Okay. All right, so what I'm gonna do now is I sent you the data on the CPS 12, okay? So what I want you to do is the following. I asked you already to get the CPS 12.tda into your Stata. So I'm assuming that you guys have Stata on your computers now. I want you to get the data on Stata now. I asked you to summarize it, okay? Use the sum command, summarize it, all right? And then what I want you to do is use the BP test to check whether we have heteroskedasticity in the fitted values, okay? Assuming errors are IID. So what I'm gonna do is, all right, so write down this because I'm going to remove my iPad. I'm going to share with you my Stata file. So you're going to get your CPS 12 DTA into your Stata. I want you to use the BP test. I'm going to open for you my do file so that you can just replicate. I want you to check if we have heteroskedasticity. We have different versions. I'm asking you to do it in fitted values, assuming errors are independently, identically distributed. Okay? I'm going to remove this now. I'm assuming that you're writing after me. I'll give you like probably 5-7 minutes, no more. And I'm going to come back and ask you, like I'm going to randomly select some one of you or a couple of students and ask you about the results, and you can tell us what do you think, what model heteroskedastic or not. So let me, yes.
My Stata sometimes on my computer it acts up. Like there'll be times where like I'll open it up and it'll get to the page itself, and then like as it's loading, it'll just close out completely. Just
Are you buying the like a version of Stata or using the Rutgers one?
I was using the Rutgers one.
Yeah, I know it has. I know about the issues about the Rutgers one. So let's see if this happens. Then maybe you can contact the help desk.
Okay.
Okay, because sometimes I know sometimes it works best on Google Chrome than Safari. So maybe this isn't something that you can try.
Yeah, I could try that one.
Yeah, but other than that, you can definitely contact someone is called Corey at help desk. He's very, very helpful guy. So he would give you like suggestions about what you can do.
Okay.
Mm-hmm. So let me, okay. So this is my do file. And what you are asked to do is you get your data, you need to run the model, okay? And yes, and then you perform, see different versions. So this one is heteroskedasticity test with IID errors. And this is the one that I'm asking you to do, okay? Okay, you guys didn't ask me this question. So your model is related to, let me write it here, okay? Because instead of me sharing my, let me go all the way here. I want you to your Y is the average hourly earning, okay? So when you get your data set, your X's are age, bachelor, and female, okay? So this is your model. You have to start by regressing average hourly earning on age and bachelor and female, and then you perform the test. And this is simply the test. Let me give you, I'll come back at 3:05. We're running out of time and I didn't do whatever I wanted to do. You guys, if you have any question while you're working, let me know, I'm here.
Miss,
Yes.
I can't even get this data to open. Like it's giving me like an error like every time I try to do it.
Is it again, you're using the one on Rutgers?
Yeah,
So have you ever tried to open it before? Like, have you ever
yeah,
practiced before?
yeah. It didn't let me open it. I don't know if I need to update my computer or something, but
Is it every time or just today?
I think it just happened to be today.
But you were able to open it before?
Yeah.
Yeah.
Hold on.
So yeah, I can help you with that. I can help you with things that are related to the commands inside Stata. So for that, you can, yes, you can contact the help desk then.
Okay.
Okay, because you need to do so before the end of this week. We
Mhm.
have a homework, and it has like second part is all about Stata.
Do the second line, the IID.
So remember, the question that I said is assuming errors are IID. So this one assumes, like, anytime you don't write IID, it assumes that the errors are IID. When you add it, you're basically dropping this assumption.
Okay.
So when I ask you assume errors are IID, you simply write it like here.
Oh, okay.
So yes, Louis, you basically contact the help desk and make sure that you have Stata working running before the end of the week. And I would suggest also that you work on the same practice once you get Stata working, and email me if you have any question.
Okay.
So you want to make sure that you can answer questions. Okay, guys, so let's see. Anybody done with the test, the results? Anyone?
Do you have to put in any variables for that, or it just the state headed? He does.
Yes, as you can see here, you have to first run the regression.
Oh.
So you have to regress the model and then perform the test, right?
Okay.
And then your Y, as I said here, down here, I mentioned that your Y is the average hourly earning, and you have 3 X's.
So you put all 4 of them in the 8 head tests.
No, when you regress the model.
Oh, okay. The 3.
And then, yes, exactly, you perform the test right after.
Okay.
How about the rest? Anybody has, how about part, have you done?
Yeah, I think I did it.
Can you share your screen with us?
Yes. Just a second.
Okay.
It says you cannot start screen share with others. Well,
You cannot share, it says?
yeah.
Okay, maybe this is something in the setting. So let me show you my do file, and then for next class, I'll make sure that I adjust this setting.
I
Okay.
think if you stop sharing yours, it may let me share mine.
If I stop sharing mine, you're saying?
Yes.
Oh, okay. Let me see that. Okay, I stopped. Okay, great. Okay, can you go over what you did and
Sure.
what do you think about the results?
So first I regressed the AHE age, mature and female, and then I did the estate test.
Yes.
I think it's heteroskedasticity because at 5% it's below 0.05.
Perfect. Yes. So as we can see, it's saying 0% probability, which is less than the 5%. And this means that there is a very small probability of constant variance, meaning that there is a small probability of homoskedasticity. The only mistake that you did is, can you see that you typed IID?
Yeah.
You're not supposed to type IID, because in my question, I'm saying assuming errors are IID. So if I want to assume the errors are IID, I do not type IID. You know, I just type state head test. Once you type IID, you basically drop the assumption of IID, you know? Exactly. That's the correct test. So in both cases, whether I have IID or not, I do have a 0 probability of constant variance, or I do have a 0 probability of homoskedasticity. Your conclusion is homoskedastic. And as you can see, guys, you don't have to go to the chi-square table. You do have the chi-square result, as you can see it here, and you do also have the p-value, and the p-value is much easier to analyze all the time, like for the t-statistic, for the f, for the chi, for anything. Okay? Does anyone have any question? Okay, so thanks, Parth, for sharing your screen. And what I'm gonna do now is I'm gonna share with you guys my iPad again. We're gonna just continue until 3:20. Of course, I was planning to do so many other things. I don't know why. At many times I get like so optimistic about what I want to cover. But this topic is important, so I don't want to skip anything. I don't want to go like fast on any of the topics. So this is a very important topic that we will use in most of our applications. All right. So what we did is we have, let me go to the main screen. And as I said at the beginning, where is it? Okay, let me write it again. So we said in this topic, we are talking about the heteroskedasticity as our first violation. So we're done with that. We did the test. We said how to detect it, different ways of detections, and then how to deal with it. So you basically use the robust standard error because it allows for the correlation and so on. Our next violation is the multicollinearity. And I don't think we have any time to cover it, but just I'm gonna give you an introduction. So multicollinearity is about the x's, right? So this one was about the error versus the x's, x1, x2, and so on. This one is about x1, x2, x3, only the x's. So if I have a model like this, yi is equal to, Parth, can you mute your mic? Beta node plus beta 1 x1 I plus beta 2 x2I plus beta 3 x3I plus ui. If I have the correlation, let me write it as R1 between x1 and x2, which is R1, 2, correlation between x1 and x2. Of course, you can write it like this, correlation x1, x2. I'm gonna just write it this way, R12 is equal to, again, the correlation between 2 and 1, which is the same, right? Is equal to 0. However, the correlation between R1 and R2 and R3 is not equal to 0. Okay, so if I have no correlation between these two, then there is no problem, right? I can estimate beta 1 easily. I can estimate beta 2 easily. I don't have any problem. However, if I do have some connection between x2 and x3, this estimation of this coefficient and this coefficient will not be accurate because they are affected by each other. So anytime I do have, like anytime I have a model, I have to make sure that I'm not using variables that are perfectly collinear where the correlation is 1. I can have some imperfection, like imperfect correlation in the model, and definitely would create an econometric problem, but we can deal with it. Okay, we can correct it. We can have ways to econometrically correct it. Okay, so the classical linear regression model, CLM, assumes, so this is the classical linear regression model, assumes no perfect multi-collinearity. We don't have any multi-collinearity in the model, okay? And if this happens, then I will not be able to estimate the variables correctly. If this happens, if this is violated, then my coefficients are no more the best linear unbiased estimator. So they no more blue. And when I check the components of blue, I know that I'm talking about an unbiased, I'm talking about consistent, and I'm talking about efficient. It's still unbiased, it's still consistent, but it's no more the smallest variance. So multicollinearity is again a variance problem. It's like the heteroskedasticity. The heteroskedasticity, what we were talking about now, about heteroskedasticity, it's a variance problem. So again, multicollinearity is a variance problem. So anytime I have anytime I have multicollinearity, I have to understand that my coefficients will not be accurately estimated, will not be the best linear unbiased estimators, and the main part of blue estimator that is affected is the efficiency of the estimator. So anytime you see me writing multicollinearity, like, what is this? Wait. So anytime you see me writing like just multicollinearity like this, I want you to remember that there are two versions, perfect and imperfect. Okay? I don't mention this. I don't deal with this because I assume that we don't have perfect. What is perfect? An example of perfect, like here, is the example that we just did. Average hourly earning is equal to alpha naught plus alpha 1, age plus alpha 2, female plus alpha 3, age plus UI. What I did here is I did repeat a variable by mistake. If I repeat a variable by mistake, like I have age and age, then I'm creating a perfect multicollinearity because age and age are 100% collinear because they are actually the same variable. So perfect multicollinearity would happen by adding the same variable by mistake. So I'm not assuming that we're doing this. But it can also happen because of another reason. The other reason is called the dummy variable trap. Dummy variable trap. What is the dummy variable trap? When I was talking about the matrix formulation of our model, I want you to, I hope I can find the slide, okay, instead of me writing the whole thing again. Okay, it's right here. Look at this. So if I write this model in a matrix form, can you notice that this is equal to 1? The vector of the intercept is a column of ones, okay? All right, so I want you to imagine that I have want you to imagine that I have a model like this. yi is equal to beta naught plus beta 1, xi plus, I'm adding a dummy, okay? And this dummy is for females. So it's called df, where df, it's gonna take 1 if the person I'm interviewing is a female, and it's gonna take 0 if the person is male, df. And suppose I also added another variable or another dummy that is called dm, where dm for males takes 1 if the person is a male and 0 if a female. So I want you to imagine that these two complement each other, right? Because if this is a female, then this is a male. If this is a male, then this is 0, 1. If this is 1, then this is 0. If this is 1, then this is 0. If this is 0, then this is 1, and so on. So both, they cannot be 1 at the same time, they cannot be 0 at the same time, right? It's either or, assuming that my gender is only classified between males and females, and that's it. So the linear combination, if I add this plus this, would give me again a vector of 1, 1, 1, 1, which would be correlated with the vector of 1 I have right here, which is the intercept. So this one is 1, 1, 1, 1. So the linear combination of these two is giving me a vector of 1 that is perfectly collinear with the intercept. So if I have, this is called a dummy variable trap. So if I have a model that I have a dummy for males and a dummy for females, you don't have to add both, right? So you can actually simply remove one of them. So suppose I remove this one. This one, if it is 0, if the df is 0, then I would definitely understand that, okay, it's a male, right? I don't have to add another variable for it. So you can simply end your model here. And this way, if this is a column of 1, this is a columns of 1s and 0s, so it's imperfectly collinear. It's not going to create a perfect multicollinearity issue. The other option that you have is to drop this one. You can have a model without an intercept. This is not a problem, right? However, I do not prefer to do so, but some people would say that that's fine for them. I prefer to always have an intercept. You can actually drop the intercept and have back your DM in your model. So your model does not have an intercept. And again, this linear combination of 0, 1, 1, 0, 0 of this dummy and the linear combination of both will not be perfectly collinear with an intercept because I don't have an intercept. So this is a way to overcome the dummy variable trap. Okay, so I'm going to end here by just giving you this introduction about, where is it? About the multicollinearity. And I said, okay, it can be perfect, it can be imperfect, it can be perfect if I do a mistake, or if I have a dummy variable trap. I assume that I'm not doing any mistake, and I assume that I'm not repeating or going into this dummy variable trap problem. All right, everyone, I was supposed to cover multicollinearity and misspecification errors. I will continue next week. And for Louis or someone else, if you have any problem with data, just try to figure it out today and do the practice, email me, or I would prefer to type on the discussion forum if you have any course-related questions. All right, everyone, so I will post for you the homework too by tonight, okay? So you would be able to see the link under week 4. All right, any question?
Yeah, you said you were gonna just open the quiz from last week for me and Ahmed for today, or
The quiz, you mean?
yeah.
Yes, I will give you. I will give you and Othman an exception. I always give each student one exception per semester about missing something.
Yeah, that's all I need. Yeah.
Okay, so just make sure that you don't miss anything else because I will not open after deadlines. Okay.
Okay.
Any other question?
I'll be having class today till like 7 is when my last class is done. So I probably won't be looking at that quiz till 7. Just wanted to give you a heads up about that.
Yeah, I usually open for 24 hours because I understand you guys have other classes and deadlines. So I'll open it. Once I open it, I'll give you 24 hours.
All right. Thank you so much again. I appreciate that.
Okay, no problem. Any other question? All right, everyone. So I'll see you next week.
See ya.
See you.